Welcome to Module 12, Electrical Fundamentals for BAS. In this module, we are going to connect what you see on a BAS graphic with what is actually happening in the electrical circuit. A point value, a status, or a command only means something when the power, reference, wiring, configuration, and physical device all agree. We are not trying to turn every BAS professional into a licensed electrician. We are building the practical understanding needed to work safely, communicate with electrical trades, recognize bad data, and avoid damaging controllers, inputs, actuators, or equipment. By the end of this module, the learner should be able to explain the main electrical quantities used in BAS work, apply basic equations, and identify common problems in real control circuits. The biggest goal is judgment. When should a BAS technician troubleshoot a low-voltage signal? When should the work stop and a qualified electrician be involved? When does a signal problem come from the sensor, the wiring, the controller configuration, the reference, or the power source? These questions are the foundation for safe and effective BAS electrical troubleshooting. BAS professionals often work between low-voltage control wiring and higher-power electrical equipment. In the same mechanical room, you may see 24-volt controller power, a 4 to 20 milliamp signal, a VFD command, a motor starter, and three-phase power status. The BAS may monitor those conditions, but monitoring is not the same as being authorized to work on energized equipment. This slide establishes the boundary. Understand the signal chain, interpret the BAS data, and know when electrical work requires a qualified person and proper safety procedures. Before we talk about transformers, signals, or motor starters, we need the language. Voltage is the potential difference, current is the flow of charge, resistance opposes current, power is the rate at which electrical energy is used. BAS problem often becomes much clearer when we ask, what voltage should be here, what current should flow, what resistance is expected, and what power is the load requiring? The equations are simple, but they become powerful when used with the correct circuit and safe measurement practice. Ohm's law is useful because it gives us an expected value. If a 24-volt DC relay coil has 1,200 ohms of resistance, the expected current is about 20 milliamps. If the measured result is very different, we have a reason to investigate the circuit instead of guessing. But remember the boundary. Ohm's law is easiest in resistive DC circuits. AC circuits with coils, transformers, motors, and drives involve additional factors. Use the formula where it applies, and do not use it to oversimplify a more complex electrical system. Many BAS energy reports fail because power and energy are confused. Power is the rate of use. Energy is the accumulation over time. A 10 kilowatt load running for 3 hours uses 30 kilowatt hours. In a BAS, a trend of instantaneous kilowatts cannot simply be added unless the time interval is correctly included. When reviewing meters or energy dashboards, always check the pulse value, scaling, rollover behavior, time-based demand interval, and unit conversion. AC and DC devices should never be treated as automatically interchangeable. A relay coil, actuator, power supply, or suppression device may behave very differently on AC than on DC. Frequency matters too. Utility power may be 50 or 60 Hz depending on region, while a VFD changes output frequency to control motor speed. In BAS work, always confirm device rating, voltage type, polarity, and frequency before connecting or replacing equipment. The transformer example is simple, but the field lesson is important. A 100 VA transformer with 76 VA connected load may appear acceptable. But actuator inrush, simultaneous movement, future additions, and voltage drop can still create problems. If several controllers reset during morning start, do not assume the network failed. Check transformer sizing, voltage under load, load distribution, and actuator behavior. A software change cannot fix an overloaded control power circuit. Dry and wet contacts are a major source of BAS mistakes. A dry contact is simply an isolated switch. It does not supply voltage. A wet contact carries or supplies voltage. If a BAS input is designed for a dry contact and someone applies an external voltage, the input can be damaged. When there is any uncertainty, stop and verify the wiring diagram, input type, voltage source, common reference, and ratings. An interposing relay is often the right tool when isolation or voltage compatibility is needed. Grounding and reference problems can make a good sensor look bad. A voltage signal depends on a reference. If the controller and device do not share the expected reference, the value can drift or become unstable. Shielding should follow the manufacturer and project requirements. A shield connected incorrectly can carry unwanted current and create a ground loop. Grounding is also a safety topic. BAS teams must know when a symptom points to an electrical design or safety issue that belongs with qualified electrical support. Analog and digital signals must be treated as complete systems. A 4 to 20 milliamp transmitter can be wired correctly and still display the wrong value if the input is configured for 0 to 20 milliamps. A thermistor can be installed correctly and still read wrong if the controller uses the wrong curve. Digital inputs and outputs also require attention to voltage, ratings, contact state, and isolation. The practical rule is simple. The device, wiring, reference, configuration, and scaling must agree. This slide brings the math into BAS decisions. A three-phase motor input calculation gives you an approximate electrical input. A 4 to 20 milliamp scaling example shows how a transmitter can produce a value of 50 psi at 12 milliamps. A transformer loading example shows why nominal VA is not the whole story. In each case, the calculation is not just math, it is a reasonableness check. Does the BAS value make sense and what might make it wrong? Here is a realistic field scenario. Multiple controllers reset during morning start. The team initially suspects the network because the symptom appears as lost communication, but the communication problem is only the result. The real cause is a control transformer voltage drop when several actuators start moving at the same time. The lasting correction is transformer sizing and load distribution, not replacing controllers or rewriting logic. This is why electrical fundamentals matter to BAS professionals. These are common mistakes that can create expensive failures. AC and DC devices are not automatically interchangeable. Transformer load is not only the normal running load, inrush matters. A dry contact input must not receive unapproved voltage. Meter data must distinguish power from energy. Analog signals need the right range, polarity, common reference, and scaling. Outputs have ratings. And grounding or shielding problems can create symptoms that look like device failures. The best troubleshooting protects people and equipment first. This knowledge check tests signal scaling. In a 4 to 20 milliamp signal, the live zero is 4 milliamps and the span is 16 milliamps. A 12 milliamp reading is 8 milliamps above the live zero, which is half the span. For a 0 to 100 psi transmitter, the expected pressure is 50 psi. If the BAS displays 60 psi, the first thing to check is scaling and input configuration before replacing the transmitter or changing the process. This knowledge check tests signal scaling. In a 4 to 20 milliamp signal, the live zero is 4 milliamps and the span is 16 milliamps. A 12 milliamp reading is 8 milliamps above the live zero, which is half the span. For a 0 to 100 psi transmitter, the expected pressure is 50 psi. If the BAS displays 60 psi, the first thing to check is scaling and input configuration before replacing the transmitter or changing the process. The assignment turns the module into field practice. Learners should identify one control panel or one AHU control cabinet and document how electrical power and signals support BAS operation. The goal is not energized troubleshooting. The goal is structured observation. What transformer is used, what signals are present, what scaling is configured, what references are required, and what risks should be addressed. The submission should include a one-page review, one screenshot or photo, and one recommended corrective action. To close Module 12, remember the main idea. Signal integrity depends on the complete electrical path. BAS professionals do not need to perform every electrical task, but they do need to understand enough to ask the right questions and avoid wrong conclusions. When power, reference, wiring, configuration, and the physical sensor agree, the BAS point can support a decision. When one part is wrong, the graphic can mislead the entire team. In Module 13, we will build on this foundation and move into motors, drives, and power quality.